I am not, in fact, trying to speak. However, I do not know why. Screen. Oh, here we go. All right. So I guess I'm presenting now.
Just bear with us 1 second. We'll get you properly introduced here.
All right.
Yep. Sorry, folks. I was trying to make sure we had the recordings all queued up to save. I'm going to hit the start recording button now. And today we have, I also want to announce we are switching over moderators, and we have the lovely Munion who will be continuing moderating for the rest of this afternoon. So please continue to ask some questions, and he will assist in answering them. And we also have today Johnny Sunshine, who is going to be presenting his talk with legacy UNIX subsystems and legacy grain bread. So this is, for most of the computer history, there has been UNIX. Along the way, we've cultivated many legacy systems that still exist today, off in some hidden corner of the UNIX file system, still usable but rarely used, mostly having been replaced with modern methods. For most of human history, there has been bread, along with the way we've cultivated many legacy grains that still exist today, off in some hidden corner of the world, still unusable but rarely used, mostly having been replaced with more modern grains. In this talk, Johnny will briefly go over some of the weird bits and bobs lying around in your UNIX that may have never been used, or in some grains lying around the world that may have never been used, and show you how to use them. So off to you, Johnny.
Hello. Hi, everyone. Welcome to my talk. If it sounds like it's slapped together in 4 days, that would be because it is slapped together in 4 days, in fact. So I want to talk to you a little bit about some old stuff because I like it. Old computers, old grains. I didn't study history, but I kind of am a bit of a history nerd. So who do I even think I am? I'm going to start with the computer part. So I grew up pulling computer parts out of the trash, putting them together. I had a 8088 well into the 386 era and a 486 well into the Pentium 2 era. So I've always kind of had old computers kicking around. I was sort of adjacent to the hacker scene. It was terrible. So people were jerks. You could never really be lead enough. So I kind of slipped into just being a programmer. being somebody who really liked old computers, I also really liked large computers. So some of the history of the way that we have created machines over time. I don't know, I just like really liked big machines. So I was a programmer. I studied comparative philosophy through college. Somewhere along the line, I took a formal logic class. I enjoyed it quite a bit. It was cross-listed with computer science, so I courses. Eventually got my degree in that, but I still have a minor in comparative philosophy with kind of a focus on like the history of ideas. So during college, being somebody who really liked large machines, Sun Microsystems open sourced Solaris while I was in about my third year of college. And this was great to me because this was a real operating system that ran on real machines. I didn't have to play with Linux anymore. And I don't mean to denigrate Linux at all on this. It was just like at the time it was from the famous like post from Linus Torvalds introducing it. It was not as real as real Unix. So this was like a real Unix that I got to play with. So I started playing with it. Eventually got a job at Sun Microsystems in their operating systems engineering group, and kind of went from there. Sun doesn't exist anymore, but while I was there, I picked up a lot of stories about how things, were put together, some of the history of why they were put together. So hopefully I can share something useful with you guys, you people, sorry. So let's start with the beginning of Unix. Unix started in AT&T Bell Labs. It started because Kernighan wanted to play video games. That's not even a joke. So the machines that they used mostly were very large, very expensive batch processing machines that cost something on the order of hundreds of dollars an hour to use. But Bell Labs had an old PDP-8 kicking around, which was this tiny machine. It was about the size of a refrigerator that was, just open for grabs. And Kernighan wanted to play a lunar lander game. It was the late 60s, early 70s. People had just landed on the moon. And so, there was a few video game simulations kicking around for machines that you could plot your own course and, land on the virtual moon. Having this machine kicking around, Kernighan decided, you know what, I'm just going to write my own. We can have some fun. It'll be great. So like all good projects, he invented a programming language and an operating system to go with it. And that operating system was Unix, which was a play on the name from Multics, which was a multi-user operating system. This was Unix because they were clever like that, I guess. The interesting part about writing Unix, though, is that he decided to write it in a high-level language, which was one that he created himself. He didn't write it in COBOL or anything. But that language was C, the C programming language. And so he wrote most of the operating system in C with some subroutines in the assembly code for the PDP-8. That machine kind of outlived its usefulness fairly early on, so it almost immediately got ported to the PDP-11, which was the successor to the 8, where it kind of lived on. And the PDP-11 became very, very popular on university campuses because it was, relatively speaking, incredibly cheap. So it sort of ended up spreading from there. So Kernighan's bored, he's playing video games, he writes this operating system, and then management starts knocking on his door, asking him, what are you doing with your time? Why are you wasting time? While he was writing it, he was writing the manual of how to use it. And the manual he decided to put like online, as in on the machine itself, rather than just printing it out, which meant inventing typesetting. a typesetting program to go with it. So that was also part of the operating system's typesetting. So that's what he sold to management. This is a typesetting program for all of the secretaries around the world so that they can make nice formatted documents to sell to other bits of management. So essentially, UNIX started off as a video game that turned into a printer. It's now 2020. UNIX is still not very good at either of those tasks, but here we are. So what happened to UNIX after that? It went to college. It met some people, and it got a job. The college it went to was the University of Berkeley, which is the university around here. It's not too far from where I live in Oakland. This photo is a photo of the University of Berkeley. So there were some, so the software at the time was distributed with the source code. It was just sort of the way things worked. You sold licenses and software licenses and source code with the software, so people could debug it and fix it and patch it and what have you. So these Unix tapes started shipping around everywhere. It was, you know, one of many options that you could use on your like brand spanking new PDP-11 if you're a college or a medium-sized to large business. And at the University of Berkeley, a bunch of people decided to start adding stuff to it. Somebody wrote an annotated guide as the Lion's Guide to Unix. The Lion's Guide, because Unix was written in a modern high-level language, reading the source code was very, very easy. Unlike other operating systems, which were all written in assembly, which, you know, pages and pages of opcodes for one minor subroutine, Unix had something in a modern language that was human readable, and the algorithms that were involved, you know, could be more easily understood. And so universities started using it as a textbook. They started shipping around in their operating systems classes and their electrical engineering classes. Here's, you know, one example of an operating system that you might want to write. It's in a language where you can understand what's going on. So lots and lots of universities started using Unix. In Berkeley, they started adding features to it. They just patched stuff onto it, added some new utilities, some new subroutines, because it was a Unix because it was open source and full of operating systems development was still a new field. They were just kind of using it as kind of a dumping ground for all kinds of experiments. They'd write new schedulers, they'd write new file systems, just kind of like seeing what would work, teaching the students and like researching different things about operating systems because we hadn't like nailed that down yet. So it kind of became a dumping ground for all kinds of little experiments, including the most important one was the TCPIP stack, which was a network communication stack that we still use as an experiment in university, as an experiment between a couple of universities. And this really opened up a lot of doors. Having networking now on an operating system used by several universities meant that you could start talking to other universities, other students in the university. The quote that I have up now, "The network is the computer," was Sun Microsystems logo or Sun Microsystems slogan in the late 90s. And it sort of was true. Because of my background of working at Sun, I know a lot more about Sun, and I don't want to say that they are the ones that like invented everything. I just know more of the background. So Sun Microsystems started as the Stanford University Network. They created a machine that was meant to fit in the network. It wasn't meant to be a standalone machine, this PDP-11 that, you know, you come in and you do your batch jobs. It wasn't even something that you log into from a serial console in the same lab so that two people could use it at the same time. It was really meant, it was built out as a network computer. And this changed a lot. So they built so many other technologies around that prospect. And let's say that you're coming out of the 80s, or I guess 70s, and you wanted to build something like that from scratch, what would you invent first? Yeah. First thing you would think is you have one big machine, one big expensive machine, and a bunch of little cheap junk machines kicking around. Because you want people to be able to use it in their lab, in their library, maybe even in their dorm room. So what might this machine want? What might you want this machine to do? So first of all, you'd want to have some storage. People have files, they have theses to write. Theses? They have, just code to run on several different machines. So they need to have files, right? So, you create a file system. NFS, the network file system. The other thing you might want is, you have several people from around the university logging into stuff. We're talking about over the network now. It's not a local thing, so you can't really rely on Unix's permissions. Like, the Unix permissions were designed for 2 people logging in on 2 different serial consoles to one machine and sharing time. But now we're talking over the network. So how do you enforce some kind of authentication, authorization scheme? And you probably want some way for users to communicate with each other. Research labs are more than just one person's plugging it away. You have several people that want to communicate with each other. They might want to be able to look each other up. One of them might be in one lab, the other one's in their dorm room. One might be in Stanford, the other's at Berkeley. So, email already existed at that time, but a way to look up other users that are using the same system that you are, which is also important if you're going to be a big file storage system, because, you have 2 different users, right, from 2 different machines writing files on one big NFS server. You have to come up with some kind of like authorization authentication scheme, some way of like knowing which users are around that you may not know already. If my name is John on one machine, how does the big machine know that? So they created SunRPC as part of the NFS scheme. So SunRPC it has a new name now. It's like Open Networks RPC or something like that. This is still in most modern Unix. This is in Linux. Like, it's around. It's used as part of the Linux NFS server. So SunRPC starts off. You've got a port mapper on port 111 that you can talk to. You ask the port mapper what services are available. It will give you a list. And it's a remote procedure call protocol. So you basically talk to it the same way you would talk to any other C function. So it's literally just a function that you call for various different port mapper things, or for various different RPC things. Uses the Unix C calling conventions, the AT&T convention. It has a data serialization format called XDR. When you are writing a new protocol, you would use RPCgen, which is an application. It's a command line utility. So you start off with a sort of protocol. I don't know how you would phrase that. You start off with a like a template basically, and it will generate some C code. You can use inetd to execute applications that use SunRPC. There's one thing about SunRPC, especially in Linux, is that there's several implementations. The kernel has one for the kernel NFS server. glibc has one. There's probably a few more kicking around. And whenever there's several implementations of something, there's always bugs kicking around. We see this like everywhere, XML parsers and JSON parsers, etc. And there have been historically a bunch of bugs in SunRPC, both in Solaris itself as well as in Linux. But this still exists in your Linux today. If you go to any random Ubuntu box, you will find implementations of SunRPC kicking around, despite it being designed for remote procedure calls on a university in 1982 or whatever. The other thing that they need, the reason why it existed is because you have these files you need to write, you have this file server, you need to be able to like connect to it, call procedures like write. And so, you know, that's why they created SunRPC. The other thing that they needed for NFS was the VFS layer. So VFS is the virtual file system layer. It has originally Unix had read, write, open, stat, a bunch of other file calls that your applications would call when they need to do work on files. And in Unix, everything is a file. And that was pretty like deeply embedded in the kernel and how that worked. So for NFS, the VFS layer was added, and this allowed people to use multiple different file systems with the same interfaces. So you could read and write, etc., and then somewhere it would end up talking to the correct one. You could use the fast file system, the proper Unix file system. It could be an NFS store, and now as an application, you didn't have to care. You just read and write to files. And the VFS layer is you know, standard. It's used for everything. There's a page cache. The block diagram I have up now is the modern Linux VFS system, sort of abbreviated. There's some more stuff in there. But you know, like it's around. File systems are the same as far as applications are concerned, and the implementation code between the kernel, VFS layer, and applications, the only thing a file system developer needs to do is write something that speaks VFS semantics. The other thing about file systems is we have kicking around something called the Automounter. This is still in Linux today. You can set it up to use automatic home directory. So if you're a new user logging into a machine, it can check the various databases and make sure your home directory is still there. It's sort of a keyed set of places to look. But so say this is the case. You do log into a machine, and you're a new user that has never touched this machine before, and it's using the Automounter to pull your home directory from another NFS server somewhere because you know you need that. There are ways to figure out who you are. Naming services. The naming services switch is still used. There's not really another way to do it. It's sort of a complicated piece of code, sort of not, kind of tied into lots of stuff. The naming services switch allows you to do things like look up aliases, Ethernet numbers, groups, hosts, like host names, passwords, shadow passwords, etc. This is a functionality that's around for NIST Plus, for NIST, the Network Information Services, which was a way for there to be a centralized repository of all the naming and emails and host names and what have you, anything to do with names, to switch between them. They're configurable, so you can talk to NIST, you can talk to LDAP, you can talk to DNS, depending on how you have it set up. You can talk to just local files, which is how most systems are set up. You assume that your username and password comes with a password file. On a default installation, this is probably true, but this is configurable. You can set it up so that instead of pulling from etc password, it pulls from LDAP, which is the whole point of the name services switch. If you are an application trying to talk to the internet, trying to talk to DNS, this is what you think that it looks like. Your app talks to a DNS server, it gets a result, and then you start talking to an IP address doing whatever it is you want. In reality, what happens is you call get host by name, goes into libc, goes to the name services cache daemon, and if there's a cache hit, it'll return. If there isn't, it goes into the naming services switch to start looking up where to start looking for this. there's potentially several services. It might look at the etc hosts file, it might look at LDAP, it might look at NIS. And if it fails at all of those, then it will start looking at the DNS. It'll go out, call DNS, come back with a result, and give it back to you. It's a lot more complicated than what you're initially sold, which is, you know, you talk to your app, talks to DNS, and then gets a result back. There's actually a lot of things going on there, and there's several daemons and several pieces of code that are involved. And yeah, I guess it's more complicated than you think. So now we have all of these facilities kicking around. And you have like random people talking to your machine, you have undergrads, you have researchers, you have support staff in a university. Boy, wouldn't it be great if we had some security? How are we going to do that? So the first sort of, I guess, facility that you may or I mean you may or may not be familiar with PAM. That's the pluggable authentication manuals or modules. PAM is a facility for authorization, session management, and there's a couple others. Session management is stuff like logging the WTemp and UTemp databases. So when you log into a machine, there's a log of who has logged in before. You can access it with last. When you log into a machine and you see the banner that says last login at, you know, whatever time, that also pulls from UTemp and WTemp. They've been extended. These are legacy files, but whatever. Unless somebody's deleted it nefariously, then this is a very primitive way of logging access for auditing later. And it still exists. The UTemp and WTemp databases still exist. What else we got? Hosts allow and hosts deny. You know, you might not want every single machine on the university network to be able to talk to your particular NFS server. Say you're the chemistry department, you probably don't want the philosophy department talking to your NFS server. They don't need to. They could, I guess. So they created kind of a primitive firewall, and these are your hosts allow and hosts deny. In the firewall, like can limit by subnet or by host name, all of which are spoofable, of course. And it can also do things by subnet or home name, or host name. So you know, if the biochem department logs in, you can log it just as auditing. And there's lots more lots more functionality kicking around in Unix that I didn't even touch on. SNMP for network management. There's all kinds of file system like access controls, extended attributes. There's lots of different ways for applications to speak to each other with, you know, shared memory, with signals, lots of stuff in threading. Yeah, there's lots going on. This talk sort of, I'm kind of fleshing out a much larger one on just more and more stuff that's in Unix that you may not have ever encountered. You may have encountered it and don't know what it does. And you know, you may not have even heard of it. Lots of stuff has been picked up over the years in Unix, all kind of stemming from the idea of, you know, one machine on a university becomes several machines on a university network, becomes commercialized, becomes operational. We've picked up a lot of cruft over the years. Unix is 40 years old. And in those 40 years, subsystems continue to exist because they're used. NIS, the Network Information Service, invented in like 1981 or whatever that was, is still around and still being used in production by some organizations, even though mostly if you're going to set up a new one, you probably wouldn't use NIS. You would probably use something like etcd or whatever. So now I'm going to switch into bread. And this is the same slide from before. Who do I think I am? My family is Russian Mennonite. They were peasants, growing like peasant farmers in Russia. Soviet Union came around. Collectivization happened. They were kulaks, so they left. They went to Paraguay, where they lived on a colony, literally a colony. It was a farm. The world kind of changed around them. They're off in the sticks somewhere, having not really known anything other than being a Russian peasant. So they did things the old way. Eventually, my family moved to Canada, where I was born. But you know, my grandmother still baked in the old way. You know, you throw a bunch of stuff into a pot, and when it feels right, you bake it. And I learned baking from my grandmother, and kind of just never stopped. Being a history buff, I got interested in what food looked like before we started getting at it. I went on a real binge on the Columbian Exchange for a while, which is when New World foods came to the Old World. Talking things like peppers did not exist in Europe prior to the 15th century. And, you know, started learning about bread. So ancient bread. This is a loaf that was preserved from Pompeii, which was the 2nd century BC. So by this point, bread was already like well in circulation. It was super common. There was bakeries. If you ever go to Pompeii, it's awesome. But there's grain mills and granaries and bakeries everywhere. Really cool to wander around. They have, you know, chunks of preserved bread from the eruption. But where did bread start? There's evidence of a primitive kind of flatbread from 30,000 years ago. Largely as starch on rocks. So it was pretty. It was evident that what was happening was bread or some kind of grain-based food was being made because they had been grinding grains. There's ground starch on rocks, so there's flour, and that was probably used for a primitive form of flatbread. So later, what happened, which we have more evidence for, is agriculture happened. There's several different kinds of there are several crops that we call the Neolithic founder crops, and these are the first things that humans started cultivating. There's 3 cereals, 4 pulses, and flax. The cereals were, you know, we found grass. Grass was edible. It made a good flatbread, so we started growing it. Those grasses are, the modern names for them are emmer, einkorn, and barley. They're all, emmer and einkorn are precursors to modern wheat. Barley is, you know, barley, you still eat it. They were domesticated in the early Holocene, so they all predate pottery. So they are found in the farming communities of the Fertile Crescent, which is the part of Northern Africa, the Near East, which is, you know, Turkey, and the Middle East. And they form the basis of agriculture for the Western world. So ancient grains. This is an example. This is 4 bowls of grains I've got here. There's emmer, einkorn, and rye and modern wheat. So the top left here is emmer. The top right is rye. The bottom left is einkorn, or sorry, yeah, the bottom left is einkorn, and the bottom right is, you know, modern, just red hard wheat. So they all look different. I think the iPhone tried to beautify this a little bit, but you can tell side to side that einkorn and wheat are fairly similar in color, with einkorn being a little bit paler. Emmer is very dark. Rye has kind of a greenish, grayish tinge to it. The 2 interesting ones here are to me anyways, are emmer and einkorn, which are the two like Neolithic founder crops. These have existed as long as humans have had agriculture, and they predate pottery. Emmer is a 28 chromosome. Okay, modern wheat has 42 chromosomes in it. Emmer has 28. It's native to the area of sort of Israel and Iran. This is where it's native to, as in like grows wildly initially. Wild emmer scatters when it hits the ground, just to distribute the seeds, whereas cultivated wheats do not. They stick together because it's easier to cultivate. Emmer is still around. It's eaten in Italian cuisine sometimes as farro, so you use it for salads and things. It was popular. It's sort of, there's thousands of years of it in hunter and gatherer culture, I guess. So this would be one of the ones that they found, fragments of on rocks from 30,000 years ago. It was really popular in Egypt. Unclear why. They had other grains. They had barley and einkorn as well. They just really liked it, I guess. It declined in popularity during the Bronze Age in Mesopotamia, switching to einkorn instead. Einkorn, which is the one on the bottom left here, is a 12 chromosome. It's a very short grain. It's about yay tall. It's not very productive. It doesn't create it doesn't have as many like seeds as other kinds of wheats for by acreage, I guess. But it grows better in colder climates and marginal soils. It was used sort of in southeast Turkey and the northern part of the Fertile Crescent. That's where it was cultivated. It does not. I don't know. It was still used until fairly recently as kind of a common grain. I've ground them into flour. I have a flour mill because I'm that kind of bread nerd. So here's some examples of some ancient flour. Here's some examples of it ground into flour. So in the bottom row is modern flours. There's white flour on the left. There's whole wheat, regular wheat flour on the center, and then the bottom right is rye flour. And then the top two are emmer and einkorn. Einkorn is on the left, emmer's on the right. So you can tell that emmer's a lot darker. It's a darker grain. Einkorn has sort of a yellowish tinge to it in ways that modern wheat does not. It's sort of brownish reddish. When you turn them into a dough, you can tell the color is even more pronounced. For emmer, super brown, super dark. Rye is, super green. And they all turn into bread pretty well. Here's two examples of an einkorn loaf and an emmer loaf that I baked the other day. And when you cut them open, they have really interesting colors to them as well. So in the right over here, I have just work of regular whole wheat. Then I have an emmer loaf up top and an einkorn loaf down the bottom. You can really tell the golden kind of yellow color that it has. These are all sourdoughs. So sourdough is the way that we would have been making bread prior to modern wheat, or sort of modern yeast. It kind of occurs naturally if you kind of just leave flour and water out. But if you want to do it on purpose, you'd get a sourdough starter. You'd collect yeast. You can just leave flour and water underneath the tree somewhere, probably with some like muslin over top of it so that you don't collect bugs as well. Once you've collected it, you can start feeding it. You feed it twice a day, about 10 grams each of flour and water. And then every other day, you throw out half of it for the first week, because what you're doing is doing a lot of germ warfare. There's really gross stuff that can actually harm you growing in there, but eventually the sourness and the yeastiness will kill it. Alcohol content gets too high. Acidity gets too high. So you want to, for the first week, create a little bit of germ warfare. It will smell to high heaven. And then after the weeks cycle through, it'll start to smell more just kind of like sour and boozy. And then you just maintain it. Just continue feeding it once or twice a day. And then you can use it for making bread. You make a levain, which is sort of you take your starter and you add flour and water to it, and you just use that for a short amount of time and then immediately bake with it. You autolyse your dough, which is soaking the flour and water, ferment it, proof it, and then bake it. So if you want to do this with ancient grain, there's a few things you need to know. The gluten exists. It exists in spelt, it exists in all the ancient grains, but it's not the right kind. So if you try to just treat it like regular flour, you just end up with a sticky mess that glues itself together and doesn't work very well. So what I do when I bake with ancient grains is I make it about 60% ancient grain to 40% modern wheat, just to get the right kinds of gluten in there so it puffs up real nice. I make a very wet dough, again, because the ancient grains don't stick well together. You want lots of moisture for lots of little air bubbles to get in there. Emmer versus einkorn. Einkorn bakes a lot easier than emmer. Einkorn, the first time I used it, I just threw some einkorn flour into some wheat flour, baked it, came out just fine. Emmer, on the other hand, makes brick loaves. It's a lot more finicky. It's a lot more like rye in baking, if you've ever baked with rye before. So what I end up doing is taking all my water and my 60% of my flour that is emmer and just soaking it together for an hour before adding like the modern flour. Sourcing and finding ancient grains is also somewhat difficult. You can't just go to Safeway and buy emmer. You can, weirdly enough, go to Whole Foods and find einkorn flour sometimes. But I buy the grains raw because one of the problems one of the issues with whole wheat flours is they have oils in them that go rancid, so old whole wheat flour tastes terrible, which is why I think that a lot of Americans don't, and this is not a slag on Americans, it's why I think a lot of Americans don't like whole wheat bread. If you look at like photos of ransacked grocery stores, the only thing left is whole wheat bread because nobody likes it. It's because the flour's old and it's gone rancid. White flour you can keep around in your kitchen for, I don't know, months. Whole wheat flour kind of needs to be used immediately, and it's similar with the ancient grains because they are not white flour. So I buy my grains whole. When they're whole grains, they can kick around a while. You can grind them yourself. I have the mock mill, which I recommend if you're going to start grinding your own grain. Grain ground immediate and then baked immediately with is like completely different than old flour. So the important part is the taste, isn't it? So einkorn is a very unique taste. It's really, really cool. I highly recommend if you can try eating einkorn and emmer bread at some point. They're super unique. Einkorn has a weird kind of like sweet nuttiness to it, like a pecan. Emmer has sort of like a deep tannic I don't know, deepness to it, kind of like tea. Like if you think tea while you're eating emmer bread versus modern bread, it's there. Wheat, it tastes like wheat. It has like a kind of like vague kind of nuttiness, I guess, closer to hazelnut. But the difference between wheat and einkorn breads are like, you definitely tell the difference. Rye I love, it tastes like rye. So if you've never baked bread before and you would like to start baking bread, I suggest starting with a focaccia. Focaccia is super easy. It's super forgiving. A recipe for focaccia is, 500 grams of flour, 350 grams of water, which is the same for lots of breads, 70% hydration, and like a third cup of olive oil and whatever herbs and spices you got kicking around. Make it, make a bread, or make a dough, put it in a pan, bake it for 500 minutes, or sorry, bake it at 500 degrees for 20 minutes, and you get a delicious focaccia. But if you want a real bread, you again would start with 500-350 ratio. You add some salt, sit there and ferment it for 2 hours, let it rise for an hour and a half, bake it at 500 degrees Fahrenheit with a tray of water for 45 minutes, and then you get bread. Tips for better bread. If you put it in a Dutch oven, you get lots and lots of heat and water. Give it a long fermentation time, let it sit out for 4 hours, beat it down, make a dough, put it in your fridge overnight. Feed your starter better, slowing if you want to bake infrequently, I bake once a week. I keep my starter in the fridge, take it out on Thursday, feed it on Friday, bake bread on Saturday. And that is about it for my time, actually. So thanks for coming. I will make these slides available online. If you want to talk to me, my Twitter is johnnysunshine. Mostly it's political these days because we live in hell world. But thank you for listening to me for the last 40 minutes.
Thank you, Johnny. Great to hear about bread and old systems. And let's see, it looks like there's a couple other minor questions. Is there a recommended maximum storage times for this type of flour?
So flour is good. So freshly ground flour is good for a couple weeks. It's like any other like fresh product. You keep it for a while, and mostly the taste will just kind of decline. You'll lose some of the like complex flavors. And if you leave it way too long, like in the order of like months, it'll start to go rancid and bitter. It's not inedible. It's just, it picks up bitter flavors as the oils go rancid.
Fantastic. And what was the name of the mill that you have?
It's the Mock Mill, M-O-C-K.
Mock, M-O-C-K.
Yeah.
Awesome.
The Mock Mill site also sells grains, but they're a reseller for somewhere called Breadtopia, which sells all kinds of random weird grains.
All right, and one last one. What kind of flour do you recommend for making starters?
Just white flour is fine.
All righty.
White flour, a little bit of rye in there if you have it kicking around. If not, a little bit of whole wheat flour if you have that kicking around. You want to add some nutrients to the starter for the yeast to kind of grow better. But if all you have is white flour, it's perfectly fine.
Fantastic. Well, thank you very much for your presentation, and we'll be switching over to our next presenter here momentarily.
Thank you.
Alrighty, so bear with me for a minute, folks, while I work this transition and blip the recording.